Okay, so I think we can probably start. So yeah, thanks. So thanks everyone for joining us this afternoon. So for this seminar, we have a talk by Pedro Linck, if that's how you pronounce your second name. And he will be giving us a talk on open quantum walk simulation. So this is a topic that I think Francesco is already quite familiar with and is published on before. And so maybe let me just read out Pedro's bio before I hand over to him. So Pedro is currently a doctoral student in physics at the Federal University of Pernambuco, which is probably a horrible mispronunciation, in Brazil. So he holds a bachelor degree in maths and physics and a master's degree in mathematics, where his research explored category theory as a bridge between algebra and topology. And currently his research focuses on quantum computing and quantum information, particularly in the simulation of open quantum systems and the application of open walks to quantum computation. So yeah, so thank you for agreeing to give this talk, Pedro, and let me just hand over to you. Thanks.
Okay, thank you. Can you guys hear me well? Okay, nice. Let me share my screen. Okay, so I'm Pedro, and I'm going to talk with you guys about open quantum walk simulation. And first, we have to have some motivation to study this topic. And one of the major challenges in quantum computing is the isolation of qubits, which is necessary for current computational models since they are based on unitaries, on the unitary evolution. So you have to, so you need a closed system, but this is not the case, never. This is never the case, actually. So there is always dissipation and fluctuations. So we need ways to deal with this physically and mathematically. We are in the NISQ era, which is the noise intermediate scale quantum era. And we need ways to model quantum computing using open quantum systems because they are the only type of systems that exist. And for this, we need to develop an area called dissipative quantum computing. So in this way, we can achieve a more versatile manipulation of the qubits, since now we are not dealing with solutions to the Schrödinger's equation. We are not dealing with an unitary evolution. We are dealing with a more general type of matrix, which is called Krauss operators. And of course, we have the possibility of simulating quantum computers and operations more realistically. Not so ideally using unitaries, but using this other type of operators. And we have lots of models for this type of computation. Models is a lot of models. And the model which I am going to talk about today is the model of open quantum walks, which, as Grammy said, Francesco is quite familiarized. Okay, so the proposal for the open quantum walk model is essentially this. You have the walk space, let's say like that, or better saying the graph space. You are moving through a graph, and you have a state space. So you move through the graph, and you change your state while you are doing this. So the total space that you are dealing with, it's a tensor product of your state and the state of the graph, the state where you are in the graph. So, well, for those who don't know, these Krauss operators, for example, suppose that you have just one. So the sum is not really a sum. It's just one term. Then you have a unitary. You have something dagger, something equals to the identity. So you have the unitary. And for open quantum systems, this is not possible since the general framework to develop the theory of open quantum systems, it's a global unitary, and you trace out the environment. So you have an evolution that is a little more complicated than just a unitary. So you have a lot of operators, such that the sum of this operator deck operator, this is identity. This is the identity. So in this case, what we have is, for each node of the graph, we have a lot of cross operators. For example, in the node, let me see, in the node 2, for example, you have two cross operators, one going to the node 3 and one going to the node 0, okay? And so we have, for this model, we have for each vertex a set of cross operators. But the cross operators are acting only on the space of the walker. He's not changing the place on the graph. So what we have to do is we have to define an operator a little bit more general than that, with are these operators M. So they apply the operator B, the cross operator, to the walker, and you change the state, the walker state, to jump from I to J. And of course, since we have a lot of these operators, we have to sum over all of them to do the complete evolution of our system, okay? Of course, if someone has some question, you can interrupt me, and so we can all learn together, okay? Okay, so this is the model, okay? But how we can actually do some quantum computation with this? How do one do quantum computation with quantum walks or open quantum walks? One way to do this, it's a simple topology, a linear topology, which does not introduce any interference effect. It's basically the mathematics of this is a Markov chain, basically a classical Markov chain. And essentially what you are doing here is you can jump from left or to right, and after you jump, you have your state changed by an unitary, for example. The first unitary, the second unitary, you can have a lot of unitaries. And you can see this, like, for example, an atom with a lot of levels, and you can jump. And for example, if you have an atom in a bosonic thermal bath, which is basically, let's say, an electromagnetic field, then you have an how do you say that? And the lower state, let's say like that, I forgot the name, the states of less energy, which is, for example, the 0, you can't go below the minimum energy, so you can stay there. And you cannot go infinitely large enough because the electromagnetic field has an energy. So you cannot gain more energy than the electromagnetic field can give you. So you have something like this, okay? You can jump and you can stay on the boundaries, for example. And this omega and lambda, these two parameters, are the probabilities of excitation and decay. So the computation is being realized on the last node here, for example. You have the composite U2 composed with U1 on the last node. So the result of a computation will be on your last node, okay? And so we have to estimate some things. For example, how much time do I have to wait to measure? For example, if I want to design an experiment, or if I want to design a simulation, how many times do I have to run this walk? How many steps of the walk do I have to take? So I can measure and have a large probability. When I say large, it's not necessarily like 90%, no, like 1/3%, one third, it's 30%, it's already big for quantum computation. It's already good. So, okay, we assume here, just for some mathematical purposes that are going to be very clear later, that omega is greater than lambda. So you go more to the right than you go to the left. Okay. Okay, let's talk a little about the mathematics of this model. As I said, the state after any steps is this state. So the only thing that changes when you go from step, for example, 4 to step 5, it's the probability. The state of the walker does not change. So the entire evolution is dictated by these probabilities, and there is no quantum interference, there is no quantum walk effects, let's say like that. It's basically a classical random walk, okay? So the probability. And the transition matrix is this. For those who don't know, a transition matrix, it's basically, for example, the first column is saying, what's the probability, for example, this first element, lambda, is saying, what's the probability of going to the first node to the first node? It's lambda. And the element below, the omega, is saying, what's the probability of you going to the first node to the second node? It's omega. What's the probability, the third now, in the first column, the third row, what's the probability of you going from the first to the third? It's 0, because there is no arrow here, from 0 to 2, for example, okay? So this is a transition matrix, and this transition matrix is relatively simple. We can indeed calculate the steady state exactly. We know how to do this using the techniques of classical Markov chains. So essentially, we have to we need to find an eigenvector of probabilities with eigenvalue 1. And so we can find this relatively easy, just do this linear system, and we find these xm's, which are the probabilities in each node m, okay? The x0, for example, is the long-term run, the steady state probability after infinity time. It's the convergence of the Markov chain is to this state. Okay, and this parameter A, I just defined it because it is convenient to treat him mathematically, so we don't have a lot of omegas and lambdas, or omegas and 1 minus omegas. This formula is quite simple, quite elegant, quite small. So we are going to use this parameter A to do some calculations. And okay, for example, this is the steady state simulation. Okay, so we have something that looks like an exponential, of course. It's just you see something like here. The parameter A, it's a to the power of m, and m is the position. So we have something like an exponential. It's okay, we expect that. And this is the steady state probability. Let's remember that. But of course, if we don't have, for example, if the omega is very small, we must need to know, for example, in the long-term run, will I detect it on the last node? Will I do my computation properly with how much probability? So the probability of success is the probability of detecting in the next node, in the last node, which is, by the formula that we calculated before, this, okay? Okay, so if we want, for example, 1/3 of success, we have to find some A or some omega such that this formula is greater than 1/3, okay? So let's do this. If we want that our probability of success in the long-term run is greater than some eta, then we have this, it's just some algebra. Then we can isolate the a's in one side and we get this, okay? Okay, this inequality, maybe, I don't know, solve it analytically, maybe a little hard, but we don't have to do this because as eta and a are positive, then a to the n-1 power is positive. And we can, for example, it suffices to ask that this term here, it's greater than 0. Because then in the left side, you have a term that's greater than 0. And in the right side, you have something that is a little less than 0, a little negative, let's say like that. So it's not a necessary condition, but it's sufficient to require this. And okay, so we know an A, and since A is a function of omega, we also have bound to omega. If we want a probability of success of at least eta, then we need to have an omega that it's at least 1/2 minus eta. And this is very interesting because it does not depend on the size of the walk. So for example, if I want a probability of success of 1/2, you calculate and you have omega equals to 2/3. So if omega equals to 2/3, if you have 1 million nodes on your graph, in the long-term run, you have a probability of success of at least 1/2 on the last node. For example, here, the omega was 2/3, and we had 50 nodes. And as you can see, in the node 50, you have a little, it's 1/2 plus some epsilon, let's say, because of course, as I said, it's a sufficient condition, not a necessary condition, so you can go a little lower on the omega, but it suffices to ask omega equals to 2/3, for example, and you have a rate of success in the long-term run of 1/2. So, okay, so now we know how to control the probability on the long-term run of success of our computation. This is a good thing, but not so good because how much time we have to wait to do this measure? What I'm saying here is, okay, if you leave your computer running and go take a shower, go make a coffee, go do something, go take a run, and then after infinity time, you come back, then, oh, of course, there is. You will measure that with probability at least 1/2. But this is not very helpful. It's more a mathematical result that is interesting on its own, but for the simulations and design experiments, this is not actually the better thing that you can do. So we need to study not only the stationary condition, but the dynamics of the system, the evolution of the system, which is exactly what I wrote here. And what about the dynamics of the system? How does it evolve? We really need to know some details, or no, we don't need? Well, I just explained that you need. Okay, so we know the details about the steady state solution, which is the asymptotic limit of the walk. Asymptotic. This is a very important word when you are dealing with computation, because asymptoticity just means that you know something that is happening when you leave it infinity time. So it's useful from a mathematical perspective, but from a computational perspective is completely garbage, okay? So for practical uses, we need to know, for example, how long we must wait before measuring the last node to have some chance of success for our computation. So for this, we are going to study the dynamics of the walk, okay? And to do this, I used some techniques from statistical mechanics, essentially, or some physical tricks that we learn when we are physicists. So, of course, suppose Pmn is the probability of reaching the nth node with n steps. So, for example, I don't know, P of 4, 7, it's the probability of you reach the node 4, the fourth node, in 7 steps, okay? I tried a lot and talked with a lot of mathematicians to try to solve this combinatorial problem with discrete methods. For the classical random walk on the line, on the entire line, here, remember, we are not in the entire line. We have 2 boundaries here, 2 boundaries that are very complicated for this combinatorial problem. So I don't know if this has a closed solution. I researched this a lot on a lot of books about graph boundary problems. There is no such thing as an exact solution for this. I did not found it. I also was not able to do this myself. So I had to search another way to deal with this problem. Okay, so the master recursive equation for this is, well, the probability of you reach the nth step in the nth node in n+1 steps is the probability that you were behind times omega, summed with the probability of you being on the front of the node and coming back, which is lambda. So this is the master equation for our system. But of course, this is a recursive equation. It's I also using discrete techniques of combinatorics. I was not able to solve it, but of course, as physicists, we always know that when we don't know how to do something, we expand in Taylor series. So the first thing that I did was forget about the boundaries. Let's say that we have a lot of nodes in such a way that I can treat it as a continuum, okay? So the graph we are going to see, since we are now thinking about the continuum, the graph, it's not graph, it's a line. So you don't have 1, 2, 3, you have an entire line of x. So m goes to x. N, which is the step. You don't take 1, 2, 3 steps. We treat the steps as a time. And of course, the one that is the step and the time, we put the delta x and delta t, okay? So now we can expand in Taylor series, as everything in physics. And we expand in first order in time and in second order in space. This is just because in space, if you expand only in first order, you lose the notion of dispersion. So you will still have an approximation for a solution, but the approximation will be terrible, okay? So we expand to second order on space to capture the notion of dispersion of this walk, okay? Okay, when you take these 2 expansions and put them on this master equation, we have an extremely common equation in physics, which is the Fokker-Planck equation. And this velocity v, it's omega minus lambda. It's a drift velocity. So for example, if omega it's 0.7 and lambda is 0.3, so you are going, for example, it's the same thing as you're saying. No, you are being pushed 7 to the right and is lowered 3 to the left. So the drift velocity is 4, okay? And okay, so the drift velocity is omega minus lambda, which is 2 omega minus 1. And this d is the diffusion, the dispersion coefficient that is saying to us how much your solution is dispersing. And when omega is greater than lambda, I say that I would assume that to be able to solve this with the techniques that already exist. And this is the solution of a normal distribution moving from left to right. So in the simulation, this is the formula. It's an unsolvable equation. This is a great thing in physics. When you have something that can be solved, it's a good hint that you're going to that you're going somewhere. Not necessarily somewhere right, but we're going to somewhere. Okay. And this is the simulation. It's exactly this. You have a normal distribution dispersing and moving left to right, and it collapses with the wall, let's say, because you have two walls. And when it collapses to the wall, it rapidly, it's just see the mean value of this Gaussian packet, okay? As long as this Gaussian packet touches the boundary, it's basically exponential, okay? So it's very fast when after the collision, the convergence, okay? So we have a way to estimate how many steps do we have to take. Well, and how can we do this? There is a simple way. The time for the mean value of the wave packet to reach the last node is the distance divided by the time. Oh, no, sorry, the distance divided by the velocity. This is the time, okay? And for example, if omega is 2/3 and n equals to 100, then we can estimate that in 300 steps, we will have some good probability of detecting our computation. Let's see if this is true. Well, in this simulation here, for example, you can see here, when we are in n equals to 250, the probability is 10%, it's a little low. But when you go to 300, here the probability is 0.3. That is 3 times bigger. So this is a good estimation, okay? And of course, you can go a little, do a little more steps of your walk if you want to get closer to 0.5, but you don't need to do this, okay? 0.3 is already good. So this is a good estimation, actually. It's a very good estimation. It worked for essentially all the simulations me and Nadia done until now, okay? Of course, I did not say that until now, but me and Nadia are working on this together, okay? So everything here is result of our collaboration. And there is some weird, let's say, estimations that I was able to obtain. It is not the most easy thing to see. For example, the velocity that I said, it's very easy to see that it works. This estimation here, it's you can control the error, while in the velocity that I estimated, you cannot, but everything comes at a cost. And the cost of knowing the error, you have to assume some things, is very complicated. It's better to stay with the other solution. And essentially here we have an exponential convergence. Here we have, let's say, linear first and then exponential. So it's linear until it reaches the last node, and then you go exponentially fast to the steady state. It's a linear plus exponential convergence, let's say like that. And you can try to use these techniques for another kind of open quantum walks. All these estimations that I put here are terrible when you use the more general Markov chain techniques. For example, what we only need, for example, 7 steps. And when you use the more general regime, you find that you need 35 steps, for example. It's 50 steps. It's these estimations, general estimations, which are the best general estimations, articles, papers published last year, this year, about estimations of mixing time in Markov chains. They are terrible. So, okay. This is an image made by Nadia, which it's an open quantum walk in this linear topology that we are working, where omega it's 0.7 and where the size of the graph is 4. So you have 4 nodes. 4 nodes means 3 unitary operators. You can jump from here to here, here to here, here to here. 3 unitary operators, 4 nodes of the graph, okay? So the probability of detecting the state in the last node, you can see that it's kind of an exponential convergence here, because you are under the assumptions that our last log estimation obtained. And here, for example, when the error is 0.05, the number of steps that you have to take is 9, and you can see that this is pretty much true. When n is 9 here, you reach 0.55, more or less, and the steady state 0.6, okay? So it's a pretty accurate estimation, but not so general as the one. And when we use our wave dynamics estimation using the velocity, we have that the number of steps 10. It's just one step more. So it is a pretty much a pretty good rough estimation of how many steps you need to take. Of course, you don't know the error with respect to the steady state, but well, it's the trade-off for simplicity, okay? Okay, and now we are going to enter in the realization procedure. Uh, that means, how can we really do this? Given a quantum computer, how can we implement an open quantum walk? So how can we simulate, for example, oh, I see here an open quantum walk and I want to simulate it on a quantum computer. How do I do this? Okay, so here is the general evolution of an open quantum system. You have an operator M that is a sum of ki dagger, which is Krauss operators. This is the definition of Krauss operators, okay? And okay, so how do you simulate this? Well, there are two main approaches to this problem, which is the Stein-Spring approach and the Snaggy approach. So here I am going to talk basically about the Stein-Spring approach and how we do a different kind of Stein-Spring dilation to gain more memory, or to use less memory than the Stein-Spring, because Stein-Spring it's the cost of the memory is pretty high, okay? So we have an work with Nadia too, using Snag simulation to simulate open quantum systems. But here we are going to we are not going to this way, okay? We are going to explore how we can use the Stein-Spring procedure here. So, okay, what is the Stein-Spring procedure? The Stein-Spring procedure dilation is basically you construct a big unitary where the first block column, let's say, the first block column is the block column formed by the Krauss operators. So you go to a Hilbert space very large. You need to, for example, if your dimension is 4 and you have 4 Krauss operators, you are going now to a dimension 16. You multiply these two numbers since you have n Krauss operators. Each Krauss operator has a dimension of the system. So if the dimension of the system is n and you have m Krauss operators, you have to go to this unitary acts on a space of dimension m times n. So it's very large, okay, very large. And in our simulations here, in our model, we have here, we have 2 times the size of the graph of Krauss operators. So in this case, for example, that is drawn here, we have 1, 2, 3, 4, 6 Krauss operators, which is the 2 times the size of the graph, which is 3. So, for example, if the state of the walker was 2 and we are on this walk, we would have to go to a space with dimension 12, which is very high. And we are going to see here that we don't have to do this, okay? We can use a way less memory to do this procedure, okay? Okay. No, okay, we can use this to construct a circuit model for open quantum walks, but we lose locality. Oh, of course, I was almost forgetting to talk about this. When you simulate all cross operators at once, you lose the most fundamental thing that you have on graphs, which is if you are on the node 1, you just have two options. You have locality. We can go right or left. While the Stein-Spring dilation does not capture this notion. It simulates all cross operators equally. It does not introduce the notion of locality, okay? And so we have to if you want to use less memory, we can explore the locality of the walk. So, okay, how are we going to do this? We propose this other unitary here. So instead of adding a lot of systems, a system very large attached to our system, we will attach a qubit, an ancilla qubit, dimension 2, and this unitary here. What is this unitary saying, basically? Well, if you are on the state psi on the node I, if j is 1, you move to right. If j is 0, you move to left. It's basically this. There is a little thing here that you may see that it's not actually just this. For example, here on the second condition, it's not just a controlled port. It's not a control gate. It's not just that. Because when you are on the last node, you have to stay on the last node, okay? So you change to make U an unitary, you have to change the control, let's say, from 1 to 0. You have to change the state of the control when you are on the boundaries. If you did not have boundaries, this problem would not exist. For example, if you have an open quantum walk that is circular, okay? Then we don't need the boundary conditions and everything stays marvelous. Except for one thing. When the model is circular, when you reach the end of the circle, when you end of the circle, it's kind of when you give a walk, a complete walk on the circle, you now are going to see some quantum interference effects. So on the circle, the circuit model is more simple, but the mathematics to describe the things is harder. So as I said, everything is a trade-off, okay? Everything is, well, it's easier from the circuit perspective, but it's harder from the mathematical perspective. And this one here is harder from the circuit perspective and easier on the mathematical perspective. Okay, so we need a way to implement this unitary. We are going to do this by parts because it's a really big unitary, okay? A really big circuit. So let's go. We need first two unitaries to control the state. So S and A are for successor and antecessor, okay? So for example, okay, there is a problem here. S applied on E, it's applied on I, it's I plus 1, not I minus 1, okay? The successor makes you jump to the right, okay? And when you are on the last node, you cannot jump to the right anymore. So you go back to 0, okay? You have to do this bijectively because S must be a unitary, so you can implement it on a quantum circuit, okay? So, okay, we have this successor function, which goes to the right, and when you are on the boundary, it goes back, and the antecessor goes to the left, and when you are on the first node and apply the antecessor, you go back the first to the last node, okay? Okay, and we also need to prepare the ancilla because if you want, when we start with an ancilla, we start with the ancilla on the state 0, but we don't want the state 0. We want that on lambda times it is on state 0 and omega times on state 1, okay? With probability lambda on state 0 and probability omega on state 1. So that we can say, since 0 goes to left and 1 goes to right, there is a probability lambda to going left and omega of going right, okay? Okay, how to move to the right? So here we are going to do an explicit example. The first line here is the Hilbert space of the Walker. The other two, the middle two, are the graph. So the graph, which has nodes 0, 1, 2, 3, you just transform this 0, 1, 2, 3 to in binary, okay? So for example, you have the node 0, 0, 0, 1, 1, 0, 1, 1, okay? So this is the encoding of the graph in the binary system. So the first node is 0, 0, the second is 0, 1, the third is 1, 0, and the last one is 1, 1, okay? Okay, so these two lines on the middle are the lines of the graph. Here the graph has dimension 4, 2 qubits, dimension 4. And the last one is the ancilla. This P is the preparation of the ancilla. And what we do here is basically, well, if the ancilla is on state 1 and you are on the graph node, on the first node, you apply U1. If you are on the node 0, 1, you apply U2. If you are on the node 1, 0, you apply U3, okay? And of course, if this ancilla is 1, you move to the right. There is just one problem here that we are going to see how to solve it later. But the problem is, okay, but if you are not on the node 0, 0, 0, 1, or 1, 0, if you are on the node 1, 1, on the last node, this circuit is saying that you are not going to affect the Walker systems, okay, but the successor is still applied. So you are going to the node 0. You are going to complete the round, let's say, complete the circle. But we don't actually want that, okay? So we have to correct this later, okay? Manually, we are going to correct this. We are going to use an ancilla qubit to do this. It's important to note that since this that I'm saying is one step, okay? After this step, we have to trace out this prepared ancilla, put another prepared ancilla and do this. So we need a lot of, for example, if we are going to do 10 steps, we need 10 ancilla prepared ancilla qubits, just like this, okay? So this is the circuit for one step, okay? The circuit for a lot of steps, the composition of the circuit for one step, a lot of times, okay? Perfect. So, okay, how are you going to do this? And how we move to the left? Okay, how we move to the left? The same way. If you are on the node 0, 1, we can go back using U1 dagger and apply the antisuccessor. Again, the only problem here is if you are on the node 0, 0, then you are going to, when you apply the antisuccessor, you are going to the node 1, 1, okay, the last node, and you don't want that, okay? So, okay, so we have a circuit that moves to the right, but gives a circle, and a circuit that moves to the left, but also gives us a circle. So how can we fix that? Well, since every unitary can be decomposed as a lot of gates and C-naughts and blah, 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 we could try to construct a very depth circuit that gives us the correct answer. But since we are using way less memory than the Stein spring dilation, we can use a little more. We are using a way less. Okay, so let's use a little more memory. Just one more line in our circuit. Okay, just one more qubit. And now we can correct the boundaries. Here, the first line of the circuit is again the space of the Walker. The two lines below are the graph. The fourth line is the ancilla qubits that is controlling the step. And now the last line is a line that's going to correct when the boundaries. So, for example, if you are trying to move to the right, you are going to, and you are on the right boundary, you are going to activate this last ancilla qubit, okay? He's going to flip state from 0 to 1. Now he's activated. And when he's activated, he applies the antecessor unitary to our graph. And then you do what you need to do. This F is this moving to the right, for example. And when you do this, you are going to apply the successor to this antecessor. So you are going to cancel the term that was going to go to 0. You are making him go to n minus 1 and then move again to n. So okay, we corrected this. And to move again the final state from 1 to 0, we apply again the DC naught, okay? So, okay, we correct the right boundary. The left boundary is the same thing, but we change these entire dots for open dots. So when it's 0, 0, 0, you apply the successor, then you do your thing, and then apply this gate again, okay? So this is the way that we can correct the boundaries. And as I said on the abstract of this talk, of course, we can generalize this exploring locality for a more general type of topology. Note that this entire talk I told about just the linear topology, and we have so much to talk about it. But we have how to generalize this procedure to a more general type of topology, which is this kind here. Each Krauss operator is proportional to a unitary. Each node has k Krauss operators, and the weights of the unitaries are the same for any node you are given. For example, here on the case where each node has two Krauss operators, you have omega and lambda as parameters and two unitaries. These unitaries can change, of course. We saw that can be for U1, U2, U3, U4, but the weights are the same. It's always omega and lambda, omega and lambda, omega and lambda, and in each node you have two Krauss operators going left in him, and of course they are proportional to unitaries. If you have a walk, an open quantum walk, where from each node you have three Krauss operators that are proportional to unitaries, for example, with waves lambda, omega, and ni, for example, and in other node, you have other unitaries, but with waves omega, lambda, and ni, and so on for each node, we can construct a similar unitary for this. We just have to use, instead of using a qubit, using a qdit, where the qdit has dimension of how many of this k, okay, of how many Krauss operators you have in a particular node. And so, of course, now you have way less memory than using the Stein-Spring procedure, because in the Stein-Spring procedure, you are multiplying by 2 times the size of the graph. And here we are just multiplying by 2 in each step. So it does not scale when you do the graph bigger. The ancilla is not scaling, okay? So it's really way less memory. Even in space complexity terms, we are winning for a constant factor against a linear factor. So it's a pretty good how do I say that? well, I forgot the word, but I think the message is clear enough, right? And of course, thank you for your attention. Here is a picture of my two cats. And if anyone has any question, please, you can talk to me. You have my email here if you need to contact me for anything, okay?
Cool. Thank you so much, Pedro, for that very interesting talk. If anybody has any questions, feel free just to unmute yourself. I think this is it's not, what is it organized as? It's a meeting. It's a meeting, so I don't think people can raise their hands, but just unmute yourself and ask any question. I had one simple question. I think on the slide where you showed the plots of the solution to the Fokker-Planck equation when you did the series expansion.
Okay.
Yeah.
Yeah.
Yes, so the second slide on your screen. In these plots, why is there this kind of zigzag? Because you said the solution is, you have this analytic solution, which is just a Gaussian that moves. Why are there, in like the plots, you have this kind of, I'm not sure how to describe, like a zigzag up and down?
Oh, okay. It's an interesting question. These zigzags up and down are because when we here, where is the model here? We don't have a probability of staying on node 1. So when he is on node 1, he receives probability for node 0 and node 2, but there is no probability of staying on node 1. So there is kind of when you go from one step to another step, there is a thing that is exactly like the image that Nadia told us here. You have something, then you stay stabilized for one step, then you move, then you stay stabilized, then you move, then you stay stabilized, because we only have movements every 2 steps actually. So every two, if you can see the odd ones here are like a Gaussian, and the even are two like a Gaussian, because there is only movement in a particular node in 2 steps. Am I clear about that?
I think so, yeah.
Yeah, this graph here is good to see this, because the probability, when you calculate the probability, you see the probability changing here, for example, when you calculate from 4 to 5, but when you calculate from 5 to 6, it's the same thing. It stays the same thing when you calculate. And when you calculate the probability to 6 to 7, then it changes, but from 7 to 8, it stays the same. So, for example, here in the last node, the probability is only changing on the n equals to 4, 6, 8, 10. So we have, let's say, like two dynamics, one for the even nodes and one for the odd nodes. So the zigzag is due to this, okay?
Okay, yeah. I had one other basic question. It's probably a simple question. Is you assume that you have no, like the initial conditions of your graph, it's completely uncorrelated. Would introducing correlations make things a lot more complicated, or
Yes, mathematically, when you introduce these quantum correlations, you are going to affect a lot the system, and mathematically you cannot treat any longer as a simple transition matrix, as I did here. I don't know where I did it.
so it's
It's
like
not so simple. It's very more complicated. The steady state, it's harder. The state of the walker is going to change, so it's not just the probability changing. You have to study how the state is changing on time. So it's a lot harder to solve things analytically. Of course, if you want to implement on a quantum circuit, it does not introduce a lot of more complicated things to do. The hard work on the simulation is already done, so you just have alter the unitaries, these kind of things. But the mathematical, analytical solutions, let's say like that, are a lot more complicated.
Yeah, because one thing I'm also interested in is these, like, they're sort of in a certain sense related to open quantum walks, which are these collisional models. And there are ways in those types of systems to kind of make things non-Markovian, in the sense of your dynamics isn't just an iteration of a map many times. Like, you know, in this open quantum walk setup, you evolve your state by just iterating a map however many times. I didn't know if there was something similar you could do in these types of models, where you just tweak it a little bit and it kind of keeps things simple to a certain extent, but at the same time produces more kind of complicated dynamics. But maybe it's harder in these types of setups.
Yeah, I think this is something we can think about, because yeah, we haven't tried to put correlations.
Yeah, I imagine it probably makes
Maybe
it a lot
there
harder.
will be, yeah.
Yeah.
I don't know if Pedro will be able to like repeat all these calculations, but maybe we can just test if there is some advantage if we put correlations.
Yeah. Okay. Are there any? Yeah. Sorry, friend. Yeah, I'll just. So Francesca is going to ask a question. I'll just mute her.
No, Pedro, thank you very much. It was a very nice talk. But I have a technical question. You know, you said at some stage that when you couldn't find an analytical solution, what physicists do is just a Taylor expansion. Yeah? And that's fine. But there's only one problem that I think we need to check. And that is usually when stochastic processes are involved, you don't do the Taylor expansion. You do something that is called the omega expansion, because the noise goes with the square root of delta t. Yeah. So you need to take into account all the square root of delta t terms. Yeah. And you know, I haven't done it in a while, but the standard guy was Van Kampen, yeah, and he invented this omega expansion. You find it probably in Wikipedia everywhere, yeah. So I would check that in your case, whether if you expand using not just the t but square root of delta t, you might get some correction, or you definitely will get some correction terms, and that might make it either better or worse. I don't know. Yeah,
Okay,
but that's something
I
that I would definitely check. Yeah.
Okay,
because
thank you.
It would make a slight difference. Yeah.
Okay.
But I like very much the implementation on the quantum computer. Have you tried it?
Yes. I simulated a lot of things. I'm trying to simulate the classifier model that Nadia was doing there when she went there.
Yeah.
I'm trying to simulate it with this model. I already have the code. I did some. Yes. I did some experiments, but I still have to do this for Nadia. Nadia asked me this some months ago, and I didn't do it yet.
Okay. There are still some months to go. Yeah, excellent. No, and when Graham introduced you, he mentioned that you are a category theory guy. Yeah.
Yeah.
Do you think one can do some magic with ZX calculus and make your circuits a little bit easier, because those multiple control gates might not so be easy.
Yeah, of course.
Yeah, it would be nice to get rid of them. Yeah.
Yeah, this is something we like. If somebody has some hint how to get rid of this multiple gates, or because we have many of them, maybe combining them, I don't know, something like this, it will be helpful.
We will ask Kishan, who is also a category theory guy. Yeah. No, but I would definitely check that omega expansion instead of the
Yeah, I'm going to do.
That might make a difference.
Very great.
Maybe it becomes much better. Yeah.
Okay.
I mute myself.
Yeah. So does anybody else have a question? Please feel free to unmute yourself. I have maybe one. It's not really a maybe a proper question, but it's more about this difference between the Stein spring dilation and this Esed-Nagy dilation. I think if I understood correctly, you said that with the Stein spring, or you mentioned the difference in the dimensionality, right? That it's more efficient to use the Esed-Nagy, but if I understood correctly, you also don't lose this kind of locality, right? Because I think you mentioned with the Stein spring that you introduce
Well,
these
I think when you combine because the thing is that Zag dilation, it's the dilation for one cross operator. It's a matrix that simulates one cross operator, and there is a way to combine all of them. It's a work that we are doing with Nadia, me and Caio. I don't know if Caio is here. He was earlier, but I don't know if you lose locality. It's a good question. I will think about it. I don't have an immediate answer. If in our combination of cross operators, if the locality you can still preserve it. It's an amazing question. Thank you.
I asked it because I don't really understand what this. I've seen this Esed-Nagy dilation used in various papers, but I haven't really looked into it in more detail. So I don't really fully understand what the differences are between
the only difference that we are seeing when when you use the Snaggy, you have a circuit that is the depth of the circuit. It's reduced a lot. You have a lot more of C0 gates, but the depth is very, very small. I don't remember the numbers. I don't know if Nadia can talk more about that because we
no,
are
by heart, I don't know them. But it's like this, like you do for each cross operator, you do a circuit, which is just, it's more efficient. And at the end, you will do some classical combination of the results. So that's why you can do it in parallel for each cross operator. So it's better than Stein spring that you need just this big unitary. But you're not preparing exactly the states of applying all the cross operators. You are reproducing the probabilistic, like the probabilistic distribution at the end.
Okay. Thanks. Yeah. Any other questions from? Yeah, sorry.
No, when we have these results, because we are just like finishing the calculations, and I hope we will start writing the draft, and then maybe I can present this, or Pedro or Caio can present this result, because it's something interesting also.
Yeah, no, Caio can present. Caio did more things than I did.
Yeah. Caio is my other student, so just to.
Okay. Yeah, it'll be interesting to have a follow-up on what you presented today. Yeah. So, yeah, thanks. So, yeah, any other questions? Wait, sorry, we have somebody else.
Sorry, here we go. Please.
So thank you very much for your great talk. I just wanted to ask in the graph of the probability versus the number of steps, I wanted to know if the 0.5, the probability 0.5, is it the steady step, or we can have, as we add the number of steps, we can have a probability that tends to 1, a larger probability.
Sorry, could you repeat it? Because my speaker is a little low.
Yes, so maybe if you go on your graph, your simulation figure. On the simulation, please. Probability, number of steps.
Here you are saying?
Yes, please. I just wanted to know if the probability 0.5, is it like a steady step, or as we increase the number of steps, we can have a higher probability?
No, as you increase the number of steps, you have a higher probability. Yes, you have.
Okay.
When you have probability 1/2, when you are going to have more steps, you are going to increase your probability. Yes. Okay. The 0.5 probability, it's a little trickier, but yes, you also have this the same idea.
Oh, okay. I also have a small naive question. It's just on slide number 4. Is it 4 or 3? Maybe.
Let me-
Where you
Here?
solve the system of equations.
Oh, okay. The system of equation here.
Yes, please. So I just wanted to know is it by definition that you choose eigenvalue 1, or you can, is it because of, so it's by
It's the
definition?
definition of steady state, because
Oh.
the steady state is by definition when you apply the transition matrix to the state, it stays the same. This is the steady
Okay.
state. It's a good question, because there is a thing that I did not really talk here, which is how can we guarantee that this is actually going to converge to the steady state probability? Okay, so it's not always that this occurs. Actually, when you have the circle design, this does not necessarily occur. It does not necessarily reach the probability. We also have a work with Nadia that we are that we are studying, that when you have the benzene ring in chemistry, the benzene ring, you see that when you do the quantum walk, it stays jumping from between two states. It does not go to an unsteady state. It's very weird that usually we like to deal with things that converge to the steady state, but there are some mathematical things that guarantees that you are going to reach a steady state. You need the walk to be ergodic and some other things. I don't remember exactly well, but essentially you can do some calculations. I did this too, and show that indeed this converges to a steady state probability. Okay.
Okay, thank you very much.
Thank you.
You're welcome.
Okay, I think if there's no more questions, then let me thank Pedro again for his talk. And yeah, hopefully we can hear a follow-up on any new results you get from this work. Yeah.